All right, so starting chapter 18, let's pretend that we're going to take a survey. Okay, a lot of times they call those polls. Okay, but we're just talking surveys. Pretend someone took a survey, polled our community, and they asked 300 people and discovered 84% of the people are excited for the new Granger High School building. Another poll taken a few weeks later said only 80% of people are excited for the new building. So some people might ask, does that mean one poll is wrong? Well, hopefully in your mind you're thinking, no, a poll isn't wrong. So then the question is, well, what happened? Why did we get different numbers when I took my surveys? Well, in your mind, you're probably thinking, every survey is different. Thinking back to our unit on surveys, if you randomly select 300 people, you're going to get a different sample one time than you would the second time. And that could explain why we have slightly different numbers. So we expect to see variation in sampling, right, due to chance. Because we are randomly sampling, every survey or every sample will be different. And so we think we're going to see small differences, right? I'm not surprised if I take one sample and get 84%, and I take another sample and I see 83%. I'm not panicking. We expect variation. So then the question is, well, how different? I said we can have small differences. Is 84% and then 80%, is that a small difference? What is believable? How big of a difference can I have before it starts getting unbelievable or strange? So to help us understand, we're going to be talking about what's called a sampling distribution. So trying to make sense of that, think distribution. That tells you how the data, or in this case the sample, would be spread out. What sort of different results will we get? And we call it a sampling distribution because it's the distribution of our samples. So let's just imagine for a moment, this is just a number line. Okay, I've got the 84% that I saw, 83, 82, 81, maybe the 80 we saw, 79. Maybe 85, 86, 87, 88, 89, and here's 90. So this just represents a number line. Imagine if I took a sample. I got 84%. I'll mark this in a different color. And then I took another sample of 300 people. This time I got 80%. Now in real life, we don't take a sample and then take another sample and take a sample. We should do one, but we're just imagining here. So then let's imagine I take another 300 people. Well, I'm going to get a different result this time. Maybe I see 85% that say yes, they're excited about the building. Then I do another 300 people. Maybe I get 84 again. And then I do another 300 people, and another, 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 and another. I do this over and over and over and over again. So we're seeing here the distribution. How would my percentages be distributed? Well, something amazing happens. And, hopefully you'll read a little bit in your textbook. Refer back to chapter 17 about the binomial distribution. This will actually start to look like a normal model. It's pretty cool. As a matter of fact, this normal model has some very special characteristics. The normal model will be centered or have its mean at P. In your brain, P needs to be the true proportion. True proportion of what? Well, that depends on your story problem. So in this case, it's true proportion of people who like the new building. But it's a true proportion. All right, so we're going to be centered at that true proportion, and we're going to have a standard deviation that we can calculate using this formula. PQ over N. Remember Q? Think back to your probability. That's just 1 minus P. All right, so suppose it's true that 84% of people really do feel excited about the new school. Okay, it's true. I have a magic crystal ball. I know for a fact 84% of people are excited about the new building. So what would the model of possible sample proportions look like? Well, it's going to look like a normal model. That's what I just pointed out on the previous slide. It's going to be centered at p, the true proportion. So I already said that was 84%. I always like to use decimal. And I can calculate the standard deviation using this formula. The square root of p times q over n. N right here is my sample size. That's how many people I asked. So 300. And if I type that in my calculator, I find that it's approximately 0.021. Okay. So I have a mean of 0.84 and a standard deviation of 0.021. So if I want to actually sketch what this model looks like, it's going to be a normal model. I actually worked on this ahead of time. Here we go. It's going to look like a normal model. Notice I have it centered here at 0.84. And to get each standard deviation, it's just like Chapter 6. I'm thinking about going up and down 3 standard deviations. And I just used my standard deviation number to do that. So how is this helpful for us? Well, remember, if we go up and down 2 standard deviations, that's 95%. So if I took lots and lots and lots of samples, 95% of my samples would give me proportions somewhere in here. So 95% of the time, I'd get something between 79% of people support the new building, all the way up to 88.2% of people support the new building. So 95% of my proportions will be in there. So that helps us think critically about this last question. What do you think about the survey that got 80%? In other words, like, are we thinking that that's a weird thing to go from 84% to seeing 80%? Is that weird? Well, hopefully you're referring to this picture. 80% would be real close to that 2 standard deviation line, but still inside it. Remember, things that are inside 95% are not weird to us. So no, this is not weird. I saw 80% just because I was sampling. I got some sampling variation, some minor differences because it's random people. All right, so can we always use a normal model? The quick answer is no. When it comes to proportions, we actually have to check some conditions. So this is specifically when we're talking about proportion. In your mind, you're thinking percentages. There are some conditions we have to check. This is not the first time we've seen conditions, nor will it be the last. First thing you want to think about, the data should come from a random sample. If we're not sampling randomly, none of this makes much sense. Number 2, our sample should be less than 10% of the total population. So in this case, I took 300 people out of our community. So 300 was the size of my sample. We could refer to this as N, sample size. And I'm asking myself, is that less than 10% of all West Valley City? Well, I certainly hope so, right? In order for it to be exactly 10%, that would mean there's 3,000 people living in West Valley, and I think we're larger than that. So we're okay there. And the third is we're going to check what's NP and NQ. N is simply the sample size, and P is our percentage. We're going to check to make sure that's greater than or equal to the number 10. Not a 10%, just the number 10. So let's see an example of that. Of all the cars on the interstate, you're thinking freeway, 80% exceed the speed limit. So again, I have a magic crystal ball, and I just know for a fact 80% of people speed when they're on the freeway. Maybe you're thinking it's higher. So the question is, what proportion of speeders might we see among the next 50 cars? So if I'm just standing there and I have one of those cool things that the police officers use to monitor speed, and I watch the next 50 cars go by, I'm not going to see exactly 80% speed, right? Because I'm taking a sample. So I'm wondering what sort of numbers might I see? Well, before we actually draw a normal model, I need to check to make sure a normal model is appropriate, and I do that by checking the conditions. So condition number 1, data should come from a random sample. Well, as a matter of fact, looking at the next 50 cars is not random. However, it is what I call representative. Representative, meaning these next 50 cars represent any 50 cars I could see on the freeway. There's nothing special or unique or weird about them. All right, so next condition is my sample, right, my sample size n, less than 10% of the total population. Well, I'm going to be looking at 50 cars. Is that less than 10% of all cars on the interstate? Interstate, the freeway. Gosh, I hope so. That would mean there needs to be at least 500 cars on the freeway. I think we're okay there. And then the last one is NP and NQ. So remember, N is my sample size. So here's N times P. P is the true proportion of cars that speed. If I multiply that, I get 40. That is definitely bigger than 10. So we're good to go there. Just to switch colors to help you keep it straight, here's this N times Q. Well, N is 50 still. Q, remember that's 1 minus P. So that's the leftover, 20%. If I multiply that, I get 10. Cutting it close there, but 10 is equal to 10. So we're good to go. Our conditions are all met. That means we can use the normal model. All right, so here was that information about the normal model. It's going to be centered at P. So my normal model is centered at 0.8. And it has a standard deviation of the square root of PQ over N. Okay, well, here we go. Square root of P times Q over N. Remember, that's the sample size. And if I put that in my calculator, it's approximately 0.057. You'll notice I tend to use 3 decimal places. Okay, so it is a normal model. That means I can draw my lovely normal model picture, which I went ahead and did ahead of time for us. So check it out, about 0.8, right? That's right here in the middle. And then I would add and subtract 0.057. So the question said, what might we expect to see? Well, 95% of samples would give proportions of speeders between, well, if I'm 95%, I'm going up and down to 68.6% and 91.4%. So even though it's a true fact, 80% of people speed on the freeway, if I saw 85%, that would not be weird. Even if I saw 90% speeding on the freeway, that's not weird. Okay, that's what we learn here. So just to finish us up, one last question. Suppose a police officer, he's in charge for monitoring speeders, and he saw only 67% of speeders during his shift, which is also 50 cars, okay, because that's the distribution we have. If you were his boss, would you believe him? Remember, it's supposed to be 80%, that's truth, and he saw 67. Well, 67 would be about here on our picture. Is it unusual? A little. Remember, between positive 2 and negative 2 standard deviations are not unusual. So seeing 67%, something that lies outside, this certainly is just a little strange. Okay? It's not likely to occur. However, you're probably noticing it's not past 3 standard deviations. So it's unlikely, but it's also not drastically bizarre. So it's a little weird. Maybe I should even say a little weird. It's not likely that he would see 67%, but I also don't know that it's quite far enough that I'm going to maybe fire the guy. So whether or not you believe him, I guess that's whatever you know about the officer and has he lied in the past. 67%, it's a little weird, a little unusual. All right, so I know you're thinking, so what? We've seen normal models before. Why are we learning this? This is the foundation for, and I mean everything, we will be doing for the rest of the year. So this is important stuff. It's building blocks to help us with what's to come.